Good afternoon. Well, today we're going to visit Albert Einstein in the year 1905. What I have up here is actually a picture of the patent office where Einstein was working at the time. This was in 1905, and this is a picture, unfortunately, does not have Albert Einstein himself in it. Einstein had to work there because, although he had graduated from college, he basically annoyed many of his professors. As a result, he could not get a letter of recommendation from any of them, and he couldn't get a job at a university or a research laboratory. So one of his friends managed to get him a job in the patent office. He was a junior patent clerk. His boss was a man by the name of Friedrich Haller, who apparently was very tolerant of young Albert Einstein, because Einstein was a very efficient worker. He would manage to review all the patent applications that were submitted to him in the morning. And then in the afternoon, his boss let him do his physics. So what you're going to see is what Einstein was doing part-time while working in the patent office. And to me, that's impressive because he published 5 major papers, many of which would have been the crowning achievement of anyone's career, and he published all 5 of them in 1 year working part-time in the patent office. He was also largely working alone because, remember, he was isolated from universities. So this is what is called his Year of Miracles. Now, what I'm going to do first is go over some historical background, because I'm guessing, do we have anyone here with a degree in physics? Oh, we have one. So I'm guessing many of you probably are not familiar with the background that Einstein was working in the year 1905. So I'm going to go over some background information so you can set yourself as to what Einstein was doing at the time. And then we're going to go over some of his papers, and I'm going to group them by his first major paper. This is the one he won the Nobel Prize for, was his work on quantum mechanics. Then he published 2 other papers, one of which was his PhD dissertation that was basically demonstrating the reality of atoms. Have to remember, this was 1900. Not all scientists believed that atoms were real, largely because you can't see them. And many physicists were like, if I can't see it, I don't believe it. And Einstein basically came up with ways to help you, in effect, see the effects of atoms, and thereby proving that they were real. And the last 2 papers were the ones he's probably the most famous for, and that lays out his special theory of relativity. So first, some historical background. Up here I have Lord Kelvin, who was one of the preeminent scientists in Britain at the time. The quote I have up there was probably not something he himself said, but it does capture the essence of what people around the turn of the century believed. More realistically, it was probably something said by Albert Michelson, who was a Nobel Prize winning physicist. He said the following in 1894. It seems probable that most of the grand underlying principles have been firmly established. An eminent physicist, who unfortunately Michelson never identified, remarked that the future of physical science are to be looked for in the 6th place of decimals. In other words, all we're worrying about are the details. That was kind of the mindset of many people around the year 1900, that we had done it all, pretty much, except for a few details. Now, this is where science stood around this time. First, we had the most successful scientific theory was the classical mechanics laid forth by Isaac Newton. Those were still being used at this time, and very successfully. One of its successes, fairly recently from this point, was the successful discovery of a new planet. And this was done by simply taking Newton's theory of gravity and predicting where a new planet must be, and then astronomers turned their telescope to that point, and lo and behold, there was a planet, showing that Newton's theories were still very successful. In addition, there was a burgeoning theory of thermodynamics. Thermodynamics basically was the foundation for the first industrial revolution. Around this time, Those theories were being refined. One of them was by Boltzmann. He came up with the famous second law of thermodynamics. You may have heard of that. That basically says that you leave a system all to itself, it will tend to the state of maximum disorder or entropy. He not only stated that, he also turned it into mathematics. And what I have up here, this right up here, is what is on Boltzmann's tomb, and that is his equation quantifying what he meant by entropy. In addition, we had this quest for absolute zero, the point at which the lowest temperature point in the temperature scale. Around this time, physicists were successfully cooling things down to near absolute zero, including finally liquefying the last gas, which was helium. And at this point, around 1900, they had reached to less than a degree above absolute zero. In addition, we had something we will spend a little bit of time looking at, is Maxwell's equations, which successfully unified together our understanding of electricity, magnetism, and optics. This successfully predicted the existence of an entire electromagnetic spectrum, something we kind of take for granted now. Namely, we know radio waves exist, we know microwaves exist, we know about X-rays, we know about gamma rays. These were just being discovered around this time. Maxwell's theory brought them all together into one unified theory. Physicists were very proud of these accomplishments. We'll look at Maxwell's equations. There are these ones right down here. Those are Maxwell's equations. In addition to scientific discoveries, those discoveries were being applied in industry. We were in the midst of the so-called second industrial revolution. The first one was where we mastered steam. The second one was where basically we're mastering electricity. This was the point at which people like Edison and Westinghouse were building the first power plants and electrifying cities. The light bulb had recently been discovered and was now being put in people's homes. In addition, we had wireless telegraph were finally appearing. The first radio broadcasts were appearing. All of those were possible because we now were beginning to understand how the electromagnetic spectrum worked and how to generate electromagnetic waves in the form of radio waves. In addition, although locomotives were around, locomotives were becoming faster, more reliable, and were crisscrossing both Asia, Europe, and the United States. Steam travel across the oceans were becoming more reliable, faster, and more comfortable. In effect, the discoveries made by science were in fact being applied successfully in industry. And again, making people feel pretty good that we were pretty much under control of what was going on around the year 1900. I keep emphasizing that because shortly we're going to find out all of this gets turned upside down and thrown into turmoil. So people were feeling pretty complacent, but shouldn't have. Now to return to Lord Kelvin. The quote I started with was probably not something he ever said. This is actually what he did say. In the year 1900, he was asked to give an address on the status of science in the year 1900. He was asked that because he was one of the most prominent scientists of the day. He identified what he said were two clouds on the horizon. When I describe them, they're going to look like, yeah, these really don't sound like big deals. And they probably weren't. However, both lay the seeds for two major revolutions that are about to occur. The first one was Maxwell said light is a wave. Well, if light is a wave, something has to be waving. Maxwell said, well, we will postulate the existence of what he called the luminiferous ether. He used the word ether because that was one of Aristotle's elements of nature. The ether existed in the heavens. This medium for light would exist everywhere throughout the universe. Has to exist in the vacuum of outer space. Otherwise, we couldn't see the sun. Michelson decided, if this is true, I should be able to detect the motion of the Earth as it orbits the sun through this ether. So he set up an experiment, and we'll go over the experiment briefly, except Spoiler alert, he could not detect the presence of the ether. This was a major failure that really upset scientists because the ether, everyone was convinced, had to exist. The Earth, we all know, goes around the sun. The Earth must be moving through the ether. We should be able to detect that. We did not. Interesting thing is, technically, Maxwell's equations do not require the existence of an ether. Everyone was simply assuming that had to exist. It was not detected. Second one sounds even more obscure. Around this time I mentioned, first time we're having electric light bulbs. Now, light bulbs we have nowadays tend to be LEDs. These are old light bulbs, which I assume everyone in this room is familiar with, the old incandescent light bulbs with the filament. The way you make the old light bulbs is you heat up a metal by putting a current through it. That hot metal then glows. Simple question is, why? Can we explain why hot things emit light? Well, hot things, that's thermodynamics. Light, that's Maxwell's equations. Put those two together, I should be able to explain how hot objects glow. You think you would, but it didn't work. This was what was called at the time the ultraviolet catastrophe, and we'll go over that briefly. And the failure actually came from one of the tenets of thermodynamics is called the equal partition theorem. That didn't work when it was applied to basically hot glowing objects. And that was a little bit disturbing. Again, these are technical problems, but these were the two clouds identified by Lord Kelvin in the year 1900. It is interesting because it was those two things that brought out two major revolutions. One is quantum mechanics, the other is relativity. Now, I mentioned Maxwell's equations. Now we need to look briefly at Maxwell's equations. And we're going to show them. Hopefully this will work. There they are. There are Maxwell's equations. I have a t-shirt with those equations on it. Any self-respecting physicist should have a t-shirt, sweatshirt, or something with those equations on it. Those are four of the most important and influential equations in classical physics. The E in those equations is an electric field. The B is a magnetic field. So I brought a little bit of demonstration with me to emphasize what we're connecting together. Electricity, that's static electricity, which we get from doing the following. Static electricity, that's the first equation. Then we have the third equation, and I brought with me, is again the magnet. B is a magnet, so it ties together static electricity and magnets. These were thought to be two completely different things. These magnets, the word magnet comes from the fact that in a certain region in Turkey, there's a region called Magnesia. There are stones there that have this odd property that if you suspend them, they always point north. Magnets are simply stones that come from Magnesia that have this weird property that also can pick up bits of metal. Electricity comes from the Greek word for amber, because if you rubbed amber with fur, it turns out you could pick up pieces of parchment. So this comes from pieces of parchment. This comes from stones in Magnesia. And for many years, people thought those have nothing to do with each other, until along comes Maxwell, who figures out I can connect all of those things together. And when he did so, one more thing, a prism. Oops, sorry. A prism. A prism was used by Isaac Newton to separate white light into its constituent colors to make the rainbow. Combine those four equations together, and Maxwell successfully managed to derive, oops, what? My laser pointer just died on me. Oh. This equation right here took two of the constants from his equations and derived a formula for a velocity, for a speed. Plug the numbers in and out pops the speed of light. Those four equations give you light. And not only that, it can explain what light is. Light is not only a wave, it is a wave of electric and magnetic fields propagating through space. That's this little diagram right here. We have an oscillating electric field and an oscillating magnetic field propagating through space in the form of a wave. We now know what light is. And we know what light is by connecting together magnets and static electricity. He also predicts not only are they in the form of light that we can see, but there is an entire electromagnetic spectrum that no one had ever seen before, all the way from radio waves to gamma rays. They're all the same thing. So he's unifying together so many disparate objects that everyone's convinced, wow, this is really, really impressive. A major achievement. Unfortunately for Maxwell, he lived and died before the Nobel Prize. He absolutely would have won one. Nobel decided we're not giving prizes to dead people. So Nobel Prizes are never given posthumously. They're only given to living scientists. Therefore, Maxwell never won one. Now, we need to take a look at one more experiment. It was actually done well before Maxwell, in the year 1802, by Thomas Young. At this time, in 1800, people were not really sure what light is. There were some scientists, Christian Huygens among them, that were convinced light was a wave. Others, most prominently Isaac Newton himself, believed light was simply a series of particles, in fact, particles that obeyed his laws of motion. Then around 1800, Thomas Young, who was himself not really a scientist, I believe he was actually a physician, did a very interesting experiment. He poked two holes in a window, in the screen on a window. So he lit two beams of light in his room. He then held some cards up to see what kind of shadows that light made, and discovered something like this, producing fringes, regions where it is bright and regions where it is dark. In order to bring this home a little bit, one of the things I like to do in my class is to show some videos, and one of my favorite YouTubers is a guy named Derek Muller, and this is him. This is an excerpt from one of his videos where he actually reproduces Thomas Young's experiment. So we'll take a few minutes and watch this video.
What's his name again?
Derek Muller. Veritasium is his website. So if you ever want to learn a little bit of physics, look up on YouTube Veritasium. He's got a whole series of really good videos on physics. He is now retired. But the channel goes on. It started with just him. He's hired more people, and now the channel is going on even though he's retired.
Experiment so simple that you could make it at home, and yet so fiddly that I have never seen it before done with sunlight.
I was thinking about doing it in a box, like a fridge box.
You could take it out on the street.
Taking it out on the street.
Could I possibly interview you guys for about a minute? We're doing a science experiment.
I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm going to place this slide above that hole. And if you look closely, you'll see that there's two openings. Very narrow openings side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the
Well, the
bottom?
obvious thing you think you're going to see is you're going to see two lines.
2 lines on the bottom of the box. 2 bright bands.
Two little lines.
Yeah,
Yeah, I think it'll be one line instead of two.
I've been expecting the whole box lit up.
probably a kaleidoscope of some
A
sort.
bunch of colors.
Probably, yeah.
Rainbow, different colours.
Yeah, have a look. You expected to see kind of one line. Is that what you see?
No.
I see dots.
How many?
It's one circle.
Well, there's one in the middle strongest, two either side.
The two on the outside are multicolored, and the one in the middle is just white.
It's kind of a rainbow.
The rainbow of colour as well.
Quite a few colours and lots of little dots.
Like there are more dots appearing.
I think I can even see more dots spreading along. Yeah, that's amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading across that way.
Either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible.
This is what Thomas Young saw. What causes it? Well, we have 2 slits, which means we have 2 waves basically hitting the screen right here. If they hit perfectly in sync, so the crest of one wave matches the crest of another wave, they add up, you get a bright spot. If, on the other hand, we have a crest of one meeting a trough of the other, I've got a high point and a low point, they cancel each other out, I get a region where it's dark. This can be explained if light is a wave. If light is a particle, I shouldn't be seeing that. Then I should be seeing just 2 bright spots opposite the 2 slits. This definitely questions whether or not Isaac Newton was right, because particles probably wouldn't do something like that. Waves should. Then along, of course, comes Maxwell and says, well, yes, that's exactly what light should do, because light is in fact a wave. It obeys these 4 equations I wrote down, and the only solution that works is a wave. At this point, scientists are absolutely convinced light must be a wave. We have a theory, and we have right here pretty incontrovertible experimental evidence, and the 2 go together perfectly. Obviously, they don't. Okay, now we're going to look briefly at the 2 clouds that Kelvin identified. The first one was the failure of the Michelson-Morley experiment to detect the ether. I had it working a second. Here we are. This is Michelson, this is Morley. One thing that's interesting is Michelson won the Nobel Prize. His partner, Morley, kind of got lost in the shuffle. I don't know why he didn't share the Nobel Prize with Michelson. This right here is their experiment. And what they did was they measured the speed of light very accurately. Here is the Earth going around the sun. We don't know what the ether's doing. Maybe it's sitting there, maybe it's flowing in some way, but whatever it's doing, in the spring, we might be going with the ether, and 6 months later in the fall, we might be going in the opposite direction. If we measure the speed of light while we're going downstream, the speed of light should be big. When we're going upstream and the light is fighting against the flow of the ether, the speed should be smaller. So what Michelson and Morley did was, at 6 months intervals, they continuously measured the speed of light, hoping at one point they'd get a big value, and at one point they'd get a smaller value, and then they would know that we're moving through the ether. Except throughout the entire year, they kept getting exactly the same number. The speed of light was never changing, no matter how we moved through the ether. This was a little baffling. Some people suggested, well, maybe the ether for some reason is moving along with us? But that would seem rather weird. Why is it moving with us? What about Mars? Why isn't it moving with Mars or Venus or Jupiter? Why would it be moving with us? This was an experiment that no one could quite explain. Everyone knew this was really important, But here, remember, we have a theory that works beautifully. Right here, not so much. That's the first cloud. Here's the second cloud. 5,000 degrees Kelvin is important because that's about the temperature of the surface of the sun. And this is the actual energy emitted by the sun. When you take classical thermodynamics and combine it with Maxwell's equations and ask, okay, what should it be glowing? There's the theory. You will notice they're nowhere near each other. Down here, they're not too bad. Out here, they're really bad. Because theory says it should go up indefinitely, off the screen. Which kind of says the sun should be radiating, I don't know, infinite amount of energy? No, that's got to be wrong. That's not even close to being right. That's completely wrong. We know the sun's not emitting infinite amount of energy. By the way, your light bulb should be doing the same thing. The light bulbs aren't quite that hot, but they also should be emitting infinite amount of energy. Obviously, something's wrong here. Take the theory, thermodynamics, combine it with electromechanics, and you get nonsense. This was known as the ultraviolet catastrophe. This region right here is the ultraviolet region of the electromagnetic spectrum, where the theory is off the chart and the experiment's way down here. So they're about as far apart as you can get. Now comes an interesting little twist. A guy named Max Planck, a German physicist, basically he knew what the answer was because we had the data. So therefore, he was able to come up with an equation that matched the answer. As a teacher, I know full well, many of my students would do the following when doing their homework problems. They'd look in the back of the book and find the answer is 12. They'd scratch their head and say, how can I finagle with the equations to get 12? And that's what they do. Basically, that's basically what Max Planck did. He knew what the answer was, and he came up with a way to get the answer. Except he had to make one strange assumption he couldn't explain. He said energy has to come in the form of light for some reason in discrete little packets, so he said. And how much energy each packet has depends on the frequency of the light. Why? Because it gives you the right answer, that's why. But that was it. For him, this was a mathematical trick he was able to use to get the right answer. Interestingly enough, this number right here, which he gave the designation H, and this is one thing I always ask, is why do certain symbols be used for certain variables? Electric field is E, obviously. Electricity begins with E, so you use electric field, you use E. Why do we use B for magnetism? I looked it up and found out Maxwell used the letter B because he said, okay, can I use M? No, M is mass, I can't use M. What other letter can I use? Can I use A? No, geometry uses that for area. What about B? He thought about that and says, you know, no one's really using the letter B. C, that's the speed of light. D, that's for differences. E, electricity. F is force. On and on and on. The first letter he found no one was using was B. So he called magnetic fields B, because no one's using B. Why did Planck use H? Pardon, does anyone here speak German? I'm going to mangle this, I'm sorry. It's Hilfsgröße, which is helping variable, helping auxiliary variable. In other words, it's a finagle factor. To him, that's what it was. It was a number he just had to tweak in order to get the right answer. He published this result because at least he managed to avoid the ultraviolet catastrophe. However, he did it by a mathematical trick and tossing in a finagle factor. So as a result, we haven't really resolved this problem. Kind of, sort of, but not really. This is important because Albert Einstein's going to show that this is not a finagle factor. It is one of the more important fundamental constants in nature. Okay, made it through the background. So now we're going to get to the first of Einstein's papers. This was published in March of 1905. Image I have here is a picture of the bound journal Annales der Physik, the 1905 edition, which has all of Einstein's papers in it. This was apparently auctioned off in 2012 for $140,000. Now, what Einstein actually won the Nobel Prize for was his interpretation of a slightly different effect called the photoelectric effect. Photoelectric effect came from, again, a prediction from Maxwell's equations. Light consists of an oscillating electric field. Electric fields, well, they applied forces on electrons. So Heinrich Hertz decided, if I take a charged object, he used metal, but I don't have a piece of metal charge, but imagine this is a metal ball and I charge it up, so I have excess electrons on it. I then shine light on that, I should be able to knock those electrons off and create sparks. Lo and behold, that's what happened. For Hertz, that simply confirmed that light, in fact, has electric fields. Then Philip Leonard decided, I'm going to study this effect in a little more detail. Up there I have a picture of Leonard's setup. Let me see if it's working here. So what he did was, this right here is a glass cylinder that's evacuated. So everything's here in a vacuum. He shines ultraviolet light through this little hole right here on this sample right there and knocks electrons off from it and manages to measure the voltage between these 2 points right here to find out how much energy is in those electrons or how fast the electrons are going. His idea is the following. If I shoot really high intensity light through here on there, high intensity light, think waves, really big waves crashing in on this piece of metal right here. Big waves should apply big forces, which should produce big velocities and big energies and big voltages. I shoot low intensity, that's little ripples hitting it. They should apply little forces, which should give small velocities, low energies, and low voltages, if light is a wave and we understand it correctly. Interestingly enough, he found out as he increased the intensity, the voltage did not go up. It stayed the same. Now, Leonard was a brilliant experimental physicist. He won the Nobel Prize in, interestingly enough, 1905 for this work. However, he was not the greatest theorist. He thought, well, what's probably happening is what we're really seeing is how much energy the electrons have inside the atoms, and all the light's doing is liberating them. And because I'm always using the same metal, all I'm finding out that when I liberate the electrons from these atoms, I'm just seeing the same energy because it's the same electrons in the same atoms. And the light, that's all it's doing is kind of knocking the electrons out and not giving them any energy. Maybe yes, maybe no. Turns out that's wrong. Philip Leonard is also kind of an interesting character. He's a German. In the 1920s and the 1930s, some unfortunate things were happening in Germany. Philip Leonard decided to join the Nazis. He became a big supporter of the Nazis and decided he didn't like Albert Einstein. He wrote off Einstein's work as so-called, quote, Jewish physics, and was one of the people that basically got Einstein thrown out of Germany and had him flee the United States. So that's sort of one of the sad parts of the background here. Now we'll take a little more look at a more sophisticated setup for the photoelectric effect. The key parts of the photoelectric effect is we have our sample here of a metal surface. We're going to shine light on it and knock electrons off, collect the electrons, we're going to count them right here. That's how much current we're producing. Current, that's how many electrons, that's numbers. We're also going to put a battery right here, we can measure the voltage. Voltage is how fast the electrons are going across or how much energy they have. so we can measure their energy and how many I produce. What I can do is I can vary the light here, as in vary how bright the light is, what is it, its intensity. I can also vary the wavelength, or what kind of light I'm going to shine. Am I going to shine red light, blue light, green light, ultraviolet, infrared, X-rays, whatever? What kind of light am I going to shine on the metal? And then we can ask, okay, if light is in fact a wave, what should I see? Then Einstein is going to say, well, what if Newton was right all along and it's a particle? What should you see? And the differences are stark, and that immediately suggests an experiment. So this table summarizes what you'd expect to see if Maxwell is right and light is a wave. So first we should see the intensity of the light, as Leonard suggested, should be the height of the wave, which should make the electrons move faster, which should produce a high voltage. Leonard discovered, no, it actually doesn't. There also probably is a minimum intensity. The waves are really small, really low brightness, really low intensity, might not have enough force to knock the electrons off. The frequency, that's how often the waves crash against that piece of metal. If they crash really frequently, high frequency light, I'll produce the electrons more often. That'll produce a larger current. If I have a low intensity, a low frequency light, that simply means the waves won't crash in there quite so often. I won't knock the electrons off quite so often. That may produce a low current. However, and this is the key thing, no matter what color light I shine on it, I should produce electrons. There's no minimum frequency that I need. These are the predictions the wave model makes. Einstein then says, well, if light is a particle, then the intensity is not the height of a wave, it's how many photons or quantum of light I'm shooting at the metal. That's the number of photons. More photons I shoot at the beam, I'm going to knock off more electrons, and I'll produce more current. So he's predicting the intensity of the light should produce not high voltage, but should produce high current. Notice, it's the exact opposite. Also, there should be no minimum intensity. Think of the following. Ultraviolet light, to Einstein, those are really big, highly energetic photons. An analogy is you're shooting cannonballs, for an example, at a stone wall. Shoot cannonballs at the stone wall. I don't care if you've only got one, you're going to knock something off that wall. Low energy photons, say red light, think ping pong balls, very low energy. I don't care how many ping pong balls you shoot at that stone wall, you're not going to do a damn thing. Therefore, if the frequency is too low, the wavelength is too long, I may produce no electrons. So there will be a minimum frequency. If I have high energy light, I will produce high speed electrons, and I will produce a high voltage. Notice all of these are exact opposites of each other. Waves are saying that intensity gives us voltage. Einstein saying no intensity will give us current. There should be no minimum intensity for a wave. Here, there would be a minimum intensity. Here, there will be no minimum. Here, the color of the light will determine the current. Here, the color of the light determines the voltage. Here, there's no minimum frequency. Here, there is a minimum frequency. They're the exact opposites of each other. If I do an experiment, I should be able to tell, is light a wave or is light a particle? Well, obviously, somebody did that experiment. Robert Millikan did. And what did he find? Einstein was completely correct. Absolutely everything he said came true. This right here is a graph of the frequency of light. This comes straight out of Millikan's article, published in 1916. And Einstein's theory is this straight line right here. The dots are Millikan's data points. They lie exactly on the theory. In addition, there's the cutoff. Light that's below that frequency produced absolutely nothing. Light above that did produce it, and the voltage went up as the intensity went up, exactly as Einstein said. Einstein predicted the slope of that line should be Planck's finagle factor. Lo and behold, that's exactly what it was. And there was also no minimum intensity needed to create the photoelectric effect. Einstein nailed it exactly correct. You might guess, since he won the Nobel Prize for it, the immediate reaction in 1916 would be applause for young Albert Einstein. Not so. The initial reaction was exactly the opposite. These are some notable people who won the Nobel Prize. Max Planck himself, the one who came up with this idea, reaction was the following: that sometimes, as for instance in Einstein's, hypothesis on light quanta, he may have gone overboard in his speculations and should not be held against him too much, for without occasional venture or risk, no genuine innovation can be accomplished in the exact sciences. So Einstein got a little overexcited. Millikan, the guy whose experiment proved Einstein correct, in the end of his paper, you would guess would sing Einstein's praises? No. Millikan says, "We are confronted, however, by the astonishing situation that these facts were correctly and exactly predicted 9 years ago by a form of quantum theory which has now been pretty much abandoned. Einstein theory is a bold, not to say reckless, hypothesis of an electromagnetic light corpuscle of energy which flies in the face of thoroughly established facts of interference," which is to say, Thomas Young's experiment where we saw the bright and dark fringes. Niels Bohr, one of the founders, it turns out, of quantum mechanics, said, "The hypothesis of light quanta is not able to throw light on the nature of radiation." So he is not being accepted here. Then in 1923, along comes Arthur Compton. Arthur Compton does a slightly different experiment I'm not going to go over, but he did the following. He said, well, if this Einstein guy is right, and light behaves like a particle, take billiard balls. What do billiard balls do? They collide and scatter off each other. Can I make light scatter like billiard balls? He did an experiment, and lo and behold, they did. So his conclusion was, there's now little doubt that the scattering of X-rays is a quantum phenomenon, which is to say, there's no doubt now that Einstein was correct. So we go from it's absurd to now, yeah, it's got to be right. Because now we have 3 experiments that clearly show that there's some quantum phenomenon going here. We have Max Planck, who thought this was just a mathematical trick. Then we have the photoelectric effect, where Einstein showed that you can only explain it with light being a particle. And now we have Arthur Compton saying, yeah, I can actually play pool with X-rays. How are we to reconcile this? Well, what we end up with is something really strange. It's called the wave-particle duality. This is where Einstein and Bohr and others put together, how do I match these two? Well, what do we currently see as light? And it turns out, not only light, electrons, protons, atoms, molecules, they all do this. This is the way, this little animation up here is the way you might be able to think about it. Namely, we have something that looks like a wave, there's a little wavy character to it, but notice it has also a size to it. This is called a wave packet. The wave-particle duality says something like light will move through space as if it is a wave. Namely, it goes through the 2 slits of the Thomas Young experiment as a wave. However, when it interacts with matter, it's chameleon-like, and all of a sudden now it switches and starts behaving like a particle. So when it's absorbed in the photoelectric effect, or radiated in black bodies, or scattered in the Compton effect, it behaves like a particle. So it's both a wave and a particle. It has this dual nature. When I was in grad school, I remember some of my professors saying, one of the issues here is the English language, or human language. Namely, we don't normally see things that do weird stuff like that. So we don't have a word for it. Turns out we have the mathematics that describe this perfectly now, Schrödinger's equation. However, we don't really have good words to describe it because in everyday life, we don't see things behave like that. It's a limitation on our vocabulary. It's not a limitation on what nature is doing. Now, in 1922, Albert Einstein is in fact awarded the Nobel Prize. Except he doesn't, interestingly enough, get the 1922 Nobel Prize. Turns out in 1921, nobody got the Nobel Prize. So in 1922, they gave him the 1921 prize. Niels Bohr got the 1922 prize. Turns out, at this point, Albert Einstein, this is 1922, he has now published all those papers in 1905. He has also, in 1915, published his general theory of relativity. And in 1919, the general theory of relativity was famously confirmed as we saw starlight get deflected by the sun during an eclipse. He is now one of the big stars in international community, and he is on a trip through Asia. Now, at this point, it's not so easy to get from Asia back to Europe to accept the Nobel Prize. So as a result, he doesn't manage to get back to Europe till 1923. And in 1923, he finally accepts the Nobel Prize. So in 1922, he's awarded the prize from 1921, and he accepts it in 1923. The Nobel Committee tells Albert Einstein, you're winning it for your interpretation of the photoelectric effect. In your acceptance speech, you may talk about the photoelectric effect. Do not talk about relativity. You did not win it for relativity. You may not speak about relativity. However, who actually hands the Nobel Prize to you? It's the King of Sweden. King of Sweden wrote a letter to Albert Einstein and said, I really would like you to explain this relativity thing to me in your lecture. Would you please? So what is Einstein to do? Who do you listen to, the Nobel Committee or the King of Sweden? The King of Sweden. So in his acceptance speech, he does in fact describe his theory of relativity. And this is Albert Einstein in July 11th, 1923, in Sweden, accepting the Nobel Prize. And in fact, I don't know who in the front row there is the King of Sweden, but apparently he was there because he wanted to learn about relativity, even if the Nobel Committee did not. Now, that's his first paper. That's the first of 5. Now, I'm quickly going to go over the next 2. The next 2 tend not to be things he's as well known for, but they're also very impressive. The second paper and the third paper deal with atoms. As I mentioned, around this time, chemists were convinced that atoms exist. Physicists were kind of like, yeah, but I can't see them. Therefore, how do I know they're real? They're not just some hypothetical model that is useful, but they don't actually exist. Einstein shows there are 2 ways we actually can see them, in a sense. This animation is what is called Brownian motion. That was the third of his papers. The second of his papers, actually, I find to be kind of interesting because it is his PhD dissertation. He actually attempted to write a dissertation several times, the first 3 of which were all rejected. One of which was his special theory of relativity. Could you imagine being on the committee that rejected the special theory of relativity as a PhD dissertation? But that's apparently what happened. So he wrote another paper. And this is where he basically tried to tie together things we can measure in the laboratory to things that have to exist at the atomic scale. He wrote this paper, got it rejected. Einstein then, he got it rejected precisely because the professors thought it was too short. So what does Einstein do? He adds 1 sentence and resubmits it, and it got accepted. Okay, Einstein's like, whatever. In this paper, he takes and ties together 2 things that you can easily see and easily measure. One is the viscosity of a liquid. Think molasses. Molasses has a lot of internal friction. It doesn't flow very easily. One can measure how much viscosity a liquid has. Second property is diffusion. Think of when you have a cup of coffee and you pour the cream in, you don't stir it, you just watch it, you will notice the cream will mix in with the coffee and it'll be a smooth, even mixture. That's diffusion. What he literally did was take sugar, put it in water, and measure what is the viscosity of basically this sugar water, and how long does it take the sugar to diffuse throughout the water. That's something you can measure. And he connected it to the fact that the water are made up of molecules, made up of atoms, and the sugar is atoms, of molecules made up of atoms. He tied it to two things that are definitely atomic in scale. The number of atoms, just known as Avogadro's number, you may remember that from high school chemistry. That's the number of atoms you have in an ideal gas at standard temperature and pressure and a volume of 22.4 liters. And that's definitely atomic. That's counting atoms. And the second thing was the quantity, was the size of the atoms. He derived two equations for the two unknowns, Avogadro's number and the size of the molecules. And you might remember from high school algebra, you got two equations and two unknowns. You can solve them. He did, and came up with the first accurate estimate of Avogadro's number and the first accurate estimate of the size of an atom. He came up with about a nanometer for the size of the atoms, which is pretty much correct. And he came up with pretty close to 6 times 10 to the 24th for the size of Avogadro's number. Professors were convinced that this at least could get him the PhD. So he was awarded his PhD. And this was subsequently published. The second thing he did was what is called Brownian motion. What Robert Brown did in 1827 was he took some pollen granules, put them in water, and looked at them under a microscope. And this is what he saw. You can see these are little pollen things, and they're just kind of randomly moving around. This surprised Brown because they're not alive. They have no means of locomotion. What's making them move? Why aren't they just sitting there? Again, this isn't really major things, but that's curious. Why are they moving? Einstein has the following explanation. Water consists of discrete molecules, and these molecules will be constantly bouncing up against those pollen granules, randomly giving it a little push this way and a little push that way. Generally speaking, they'll be hitting them from all sides evenly, but every now and then the force will be unbalanced, pushing it one way, pushing it another way. He then uses some statistics to try to estimate how far will they be pushed in a given amount of time. And he comes up with a formula. I'm not going to produce the formula, but he does a formula and he says, well, if the molecules are about 1 micron in size, and the water is at about 17 degrees Celsius, or about room temperature, 63 degrees Fahrenheit, these should move about 6 microns in a minute. That's something I can test. And a guy by the name of, next slide. Oh, come on, next slide. Jean Perrin decided to do just that. And what he did was he suspended particles about 5.2 microns and observed them every 30 seconds. So he plugged those two numbers into Einstein's formulas and calculates how far should they move. He then sat looking through a microscope at these little particles suspended in water, watched them move around, and he charted them. And that's what these are right here. These are from his article. And what Einstein is predicting, what is the average size of each one of these segments? Notice they're all different, because it's all done randomly. But he predicts what is the average of those lengths. And what Perrin did was he actually sat down and measured each one of those line segments, measured their length, calculated the average, compared it to Einstein's prediction. They were dead on. Suggesting that, yes, the reason for these random motions of the Brownian motion is because they're being randomly hit by water molecules. Only way that is true is if water molecules are real. Water is actually made up of discrete things called molecules, which are made up of atoms. And this is something we can see. So we can effectively see atoms through this. So he manages to connect together atoms with something that's observable. After this, people have to admit, yeah, I guess these atom things are real. Would this have won another Nobel Prize? I don't know, but it was certainly an impressive accomplishment. Much of this was complicated mathematics that I didn't bother to go through. Okay, that's all I'm going to do today. Next time we'll look at the special theory of relativity, his last two papers. Do we have any questions? Yes?
So this Brownian motion experiment, I agree, convinces you that molecules are real. How does that show that atoms are real?
Well, basically the idea of the atomic theory is just that matter is made up of discrete chunks. And this shows they're definitely made up of discrete chunks.
So those chunks could just be molecules and nothing small.
True, but if you combine that with what chemists knew, then I can break those things up into hydrogen and oxygen, suggests that those chunks have to have some internal structure, namely the hydrogen and the oxygens. I can split those apart. Yes?
What is the continued source of energy in that motion?
Temperature. The water is at a temperature, which means the water molecules are randomly moving around. Yes. Haven't looked recently, but I believe the record is within like a billionth of a degree. The fourth law of thermodynamics kind of postulates that in no finite sequence of steps can you ever reach zero. And a finite number of steps, which is all we can ever do, you can only reach a fraction of a degree. And that's all that's happened. So like, I believe it's on the order of a billionth of a degree. Yes. Probably not. Probably not. But obviously, if you increase the temperature, then they're going to move around more. That's why you had to specify the temperature. Other questions?
Probably in a certain linear range. It actually doubles for every 10 degrees.
Yeah, everything's linear in a small enough region. Yes. Yes. Other questions? Okay, then I hope to see you again next week, and we'll look at the special theory of relativity. Thank you.